Okay, so continuing from last class, so basically we were trying to figure out the expansion fan in a shock tube, right? And we kind of began studying the method of characteristics so that we can study the change in properties, okay, behind and in front of the expansion wave, as well as the property changes within the expansion fan. Okay, so we stopped kind of till the last lecture, where we just at the point where we were about to find out relationships for the property changes within the expansion fan and behind and in front of it. So let's go ahead and continue from there and see where we go. Okay, so just to remind you, this is what we had, right? So we had, this was our shock tube, right? Just drawing this half of it. So then this was region 4 and this was region 3, and we had an expansion fan, right, moving into this quiescent flow, quiescent region, right? We had that, and all these waves basically originating at a single point. So we found out that if I were to draw an xt curve, right, if I were to draw an xt curve, so if I were to draw an xt curve like that, okay, then I could actually represent these waves on this xt curve this being the head of it, which is this, right, and the other being the tail of it, which is this, okay, and essentially these are okay. So this was our these were characteristic lines. Okay, these are lines in which the governing equations have their solutions. The solutions to the governing equations lie along these lines, and hence characteristic equations. Okay. Now we also talked about, and we said that the slope of this, okay, slope of this was basically u minus a, right? Yeah. Okay. Sorry. So u by a, and this was, so therefore this, the head, as you can see, is moving into region 4, and this is region 3. Okay, this is region 3, and so therefore the slope of this becomes that, and this becomes slope of that. Okay, that becomes, okay. Now in this region is 0, isn't it, because this is quiescent. So therefore this is minus 1 by a4. So this is where we had stopped. Okay, so this is essentially the, as you can see, the wave is basically centered. This is at t is equal to 0. Okay, centered, and we also showed that these, okay, so these are the C minus characteristics. Okay, and we also drew see, these could be possible C plus characteristics. Okay, and essentially what we see over here is we also talked about whether these characteristic lines would be straight lines or it could be curved, right? Now in a general case they don't have to be straight lines. Okay, for this particular case we proved that yes, these are straight lines. So hence we said that in a shock tube essentially what we have is a centered simple wave. Okay, centered simple wave, simple because it's a straight line, and centered because it's centered. Okay, and we also found out that we also said that on C minus, okay, the C minus corresponds to J minus, okay, these were the Riemann invariants, okay, and on C plus corresponds to J plus. Okay. So, we then showed that along the C plus for such a case, the J plus is well, J plus is constant on any C plus characteristic, but then we took two C plus characteristics, and we showed that essentially within the expansion fan, J plus is a constant, right. So, therefore, let us start from there. So, say what we are basically saying is that right. So, within the expansion fan, J plus is constant. So, which means that I can take any point out here for any positive characteristic, and I will have the same J plus. And so, let us do a thing, let us apply this for a point within the expansion fan and a point in, say, region 4. So, now J plus is essentially, right. So, J plus within the expansion fan, so is equal to U plus 2A by gamma minus 1, right. This is a constant, and the J plus, if I apply this, I apply to region 4, then what I get is that this is, say, within the fan, right. Okay. And J plus is U4 plus 2A4 by gamma minus 1. Okay. This is in region 4. Okay. In region 4. Okay. So, therefore, basically if I what I am saying is, let us say consider a region A here, let us consider a point, say P, let us consider a point, say Q. So, say Q, so it says J plus Q and J plus P, right. Now, they both lie on the same characteristic. Okay. So, therefore, from here what I can find out is that so they lie on the same characteristics, so J plus is going to be constant. So, therefore, I can say right. So, now from this what we can get is, if I sort of work with this, what I get is this. From this expression what I will get is this. Okay. So, we get this sort of an expression. Okay. Let us say call this as 1. Okay. Now, basically what we are trying to do here is find out properties, right, find out the relationship properties within the expansion fan. Now, what we know is that right, and what the relationship that we have is A by A4, right. So, therefore, I can now therefore write. So, from this basically what I can write is T by T4. Okay. So, you could sort of do that yourself. Okay. So, this is T by T4 is 1 minus gamma minus 1 by 2 Okay, so what is interesting here is that this is the any local velocity within the fan, isn't it? This is a local velocity within the fan, and this is the speed of sound into the in the region into which the fan is advancing. Okay, and this is where the flow is stagnant or quiescent. Okay, so similarly, now since this is an isentropic it's an isentropic process. So again we will have this. Okay. Okay, so now you can see from here, so therefore we can write P by P4. Okay. So therefore, P by P4 we will get these two relationships here now. So P by P4 therefore becomes, I am just rewriting that, this is for completion. Okay. Okay. So this is the relationship of the pressure. Okay, this is a relationship of the pressure, and let us also write the gamma. So and sorry rho. So rho by rho, those densities is essentially equal to this T by T4 to the power 1 by gamma minus 1. Okay, so which is I thought this should be 2 by gamma minus 1, okay, to the power of gamma, okay, and the rho by rho 4 should be equal to 1 by gamma minus 1. Okay. Okay, this should be, I think this should be this, okay. I think this should be this. Okay. So I'll have to cross check that if I'm getting that wrong or not. So I'll just cross check that. You can check it also. This should be given in any standard book, so just check this. I think this should be 2 by gamma minus 1, but I see in my notes I've written 1 by gamma minus 1, so you just have to cross check that. Okay. So essentially what we've done now, okay, so therefore what we have done now is got an expression for the properties within the expansion fan, right. So we have a this is the temperature within the expansion fan, this is the pressure within the expansion fan, this is the density within the expansion fan, and these all are with respect to the temperature, pressure and the density in the quiescent region. Okay. So having done that, now let us see, now this is a velocity u which is within the expansion fan. Okay. Now let us see, now we know that within a C, say C minus characteristic, so we have a C minus characteristic here where J minus is constant, and the slope obviously is the dx dt, isn't it. So u minus a, isn't it. So dx on a C minus characteristic, okay, now dx dt is u minus a, which means that essentially right, if I do this, now let us look at this here, this equation here, and therefore from here I am going to write x using equation 1. Okay. So, where I can basically get rid of this A. So, if I do that, what I get is this. Okay. Now, what is interesting this is an interesting result. Okay. So, what we see is that the local velocity is given in terms of the speed of sound in the region into which it is moving, which is the quiescent region, and x by t. Now, what you can see from here, and also you should sort of cross check yourself, that right. Okay. So, essentially what you are saying is that the x by t here, right. So, that is u3 minus a3, which is here, right, and it is minus a4, which is in this region. So, all we are saying is that basically the inverse of slope, okay, which is here, inverse of slope is essentially the u3 minus a3 in the region 3, and here it is u4 minus a4, but this is quiescent, so it becomes minus a4. So, this is a limit. Okay, this is a limit of the x by t. So, what this is essentially giving us an idea is the range of the expansion fan, in the sense that within a given time, more or less what would be the distance to which this disturbance will travel. Okay. So, this is what we get from here. Now, okay, before we sort of plot this, okay, before we look at this and see how they look, now let us go and find out how we are going to calculate the relations in this region and this region, because especially in this region, because now we have done the other part of it, okay, where we had the contact surface moving. Okay. Now, let us draw that. So, we had, this was the shock part of it. So, we had, this was the contact surface. Now, this was, we said, moving with up, right, and we had a shock wave, and that was moving yet into another quiescent region. So, this was region 2, and we said this was moving with, yeah. So, this is equal to u2 actually, isn't it? And this was moving with, say, a velocity w into a quiescent region. Okay. So, now the thing is, we have adequately calculated relations in region 2 and 1. So, we kind of know relations in region 4. Now, we are still left to find out relations in region 3, and we have now found out expressions for the properties within the expansion fan. Okay. So, to do that, now here u3, now once the diaphragm is broken, this is the original location of the diaphragm, is, it sends out a shock wave which induces motion in the fluid behind it. Okay. So, in this case, therefore, now this is a contact surface. Now, as we said, it is like a slip surface. So, therefore, the pressure across it is the same. So, we have said that P3 is equal to P2. So, it would mean that U3 is also equal to U2, right. So, having said that, so essentially what we get from here is that U3 is equal to U2 is equal to UP. Okay. So, if I do that, okay, so let us say some now, and as we have said that it does not need to be the same fluid, it could be two different gases, right. So, let us say we are going to say call the gas in or the region 1 and 4, say corresponding gamma is gamma 1 and gamma 4. So let's just say for a generic case that the the ratio of specific heats is 1 and 2. So we have two different sort of gases. Okay, now this is something now UP. So therefore, so this is okay. Now this is what we did earlier, okay, with the shock wave. This is what we did earlier with the shock wave, and you can see that this is dependent on the pressure ratios in the regions 1 and 2, right. Okay. So we had a value, we had an expression for the velocity, which is u2 up, right, in terms of the pressure ratios in the regions 1 and 2, okay. And in this case we are basically considering the gas in region 1. So therefore, this is what we have from the shock analysis which we have done before, okay. Now what we will do is we will use this equation, the pressure equation here, okay. Now you can see that this is pressure equation here, and we will apply it to anywhere between the head and tail of the expansion wave. Okay, so this is the pressure anywhere within the region, anywhere within the expansion fan. Okay. So if I look at this fan and I apply this between the head and the tail of it. So head is this region which is P4, and tail is essentially this region, so which is P4, sorry, P3, okay, this region. So what I'm going to do is apply this equation 3, okay. So equation 3 between head and tail of the fan, right. If I do that, so essentially what will I get? What I get is this. Okay. Okay, yeah. So let us write the gammas out. So we will write it this way. Okay, gamma 4, gamma 4, gamma 4. Okay, so we get this. Okay, now what we will do is we will solve for u3 from here. Okay, we solve for u3 from above. Okay, if we do that, what we get is this. Okay, so 1. Okay, so I just solve for u3 from this expression and I get this, right. But of course, we know that P3 is equal to P2. Right, because this was the contact surface, we said that there. So therefore, here P3 is of course equal to P2 as well. So essentially, this becomes the relationship. So u3 is to u3 we get in terms the velocity in region 3, we've now got in terms of velocity of sound in region 4, the pressure in region 2 and region 4. Okay. So we've got u3 here. Okay, let us look at this now. So essentially, this is my u3. Okay, and we have u2 from here. And we have u2 from here. So all we will do is now equate u2 and u3 because these are the same. Okay. If I do that, then what I get is this. So, say coming back to this here, okay. Now, if I do that, if I equate that, okay, this slightly longish kind of thing, so I will just sort of write it out, be a little patient. So P4 by P1, okay, okay, A1 by A4, okay, okay, and all of that is raised to okay. So, if all I have done here is essentially equated u2 and u3, and this is what I get. Okay. So, you can see that this relationship, when I equate these velocities, this relationship is all given in terms of the pressure ratios. So, now P2 by P1 is the incident shock strength, isn't it? So, for a shock tube, unlike in the shocks which we have done before, in such a case the strength of the shock is driven by the pressure ratios across the across it. So, which is what we see over here, right? So P2 by P1, P2 by P1 is basically the incident shock strength, right? Right, and what is P4 P1? This is essentially the P4 by P1 is essentially the pressure ratio across the diaphragm. Okay, so this is say diaphragm pressure. Pressure ratio. Okay. Okay. Now the point here is, if you look at, say, if you look at this particular expression over here, so now for a given diaphragm pressure, okay, and for given specific ratio of specific heats of two different gases in the two in the two sections, which is 4 and 1, you can actually calculate the strength of the incident shock wave. Okay, directly from this expression, Okay. So, therefore, let us sort of look at I will just illustrate point by point as to sort of how will we go about this. Okay. Now, so now we are in a position where we can essentially solve for properties in the entire shock tube. Okay. Let us see that. Now that we have found we have an expression, say like this. Okay. What is the first thing we do? Okay. So I will leave these expressions over here. Okay. So let us say okay, so let's say over here. Okay. So first things first, of course. Okay. So first things first is that for a given diaphragm pressure, okay, for a given diaphragm pressure, so let's call this equation something, okay, say 4, let's call this 5, okay. So for given diaphragm pressure ratio, which is P4 by P1. So, you evaluate or calculate incident shock strength right. You can see from here directly. So, for a given pressure ratio, diaphragm pressure ratio, you can calculate the incident shock strength P2 by P1 using 5, okay, this particular equation. And then, as we have already done for shock waves, once you get, if for an unsteady shock structure like this, for an unsteady structure like this, the properties basically depend on the pressure ratio, unlike the steady cases which we have done before, where they were dominated by the incident Mach number. So, therefore, once we have calculated the shock strength, we can totally calculate the properties across it, right. So, yes, so using the shock, so for the corresponding to so P2 by P1, we calculate all shock properties. Okay, so we can calculate all the shock properties. Okay. Now, once I do that, now what I need is essentially P3 by P4. Okay. So, P3 by P4, or the strength of the expansion fan. So, I mean see, that is easy to do. So essentially P4, so I will just write that as you can see P3 by P1. P1 by P4, but then this is P2. So, which is P2 by P1 So, now P3 by P4, if you see, this is the region. So, P3 by P4 is given by this. Okay. Now, P2 by P1 is known at this point of time, and this was given. So, then this is your expansion shock strength, sorry expansion fan strength, right. So, this is your fan strength. Okay. So, now what we will calculate is the properties, right. Now, within the expansion fan, now that we know P3 by P4, right, if we know P3 by P4, so let us go back to these relations over here. So, if you look at this, now P by P4 here, okay. Now, what we can do now is essentially use isentropy, okay, use the isentropic relationship, okay, which is okay, it's here, okay, I have it written over here. So, when I have this relationship over here, okay, so but at this point of time what I have found out is P3 by P4, okay. So, let us now calculate the properties in region 3 and region 4, okay, in region 3 and region 4. So, we are not talking about the inside the fan, we are just talking in these in the region behind and front of the expansion fan. Okay. So, now this is the isentropic relationship. So, now if I apply this, okay, now here P3 by P4 is what I have just calculated. So, P3 by P4 is known, and therefore, you can calculate the density and temperature ratios. Okay. So, that can be done, and after that what we need is properties. So, what we need is properties within the fan. So, within the fan we use equations, say 3, 4 and what? Oh, so 2, 3 and 4. So, within the fan then we shall use these equations. So, this is for within the fan, my temperature is this, temperature ratios is this, 3 and 4. So, with using those equations I can calculate for the properties within the fan. Okay. So, that pretty much gives us a solution for the shock tube. Okay. So, now let us just sort of go back to the picture that I had drawn right at the beginning, which you did not have any way of sort of deciding whether it was correct or to agree with it or not agree with it. So, let us sort of revisit that one more time. Okay. So, essentially what I am going to try and do is plot the pressures, temperatures and densities, okay, and velocity, and see if what I had drawn right at the beginning is something that you agree with. Okay. So, say okay, this is a little asymmetric, but that is okay. Let us draw it over here. Okay. Okay, so essentially this is my shock tube. Okay, so essentially this is my shock tube. This is my shock tube, isn't it? Okay, so now let us just draw this. So, let us say okay, and I am going to concentrate, just this is something that we have done before, right. Let us just concentrate on this region till here. Okay. So, this is in region 3 and region 4, which is what we have been studying in the past 1 or 2 lectures, right. So, this is basically the regions concentrating in front and behind of the expansion fan. Okay. So, if I do this, so let us mark this out. So, this is the head and this is the tail. Okay. Now, if I do that, okay, let us take a different color. So, if this is it, so let us say this is, let us call the velocity. Okay. Now, you can see that the velocity here is 0, isn't it? Its u4 is 0. So, therefore, this is 0. Okay. This is 0, and then in u3, okay, so u3 is some velocity which is given by the expression. So, it is some velocity, it is some positive velocity. Okay. So, this is essentially u3, and at this point it is equal to u2 over here. So, we are not going beyond that. So, this is u2 essentially. So, u3. Now, what is left to do is what is happening inside the expansion fan. Okay. So, let us see if we have any relationship for the velocity within the expansion fan. Okay. So, if we go and look at it, okay, if you go and look at this, we just wrote out the equation some time back. So, what we had was, okay, what we had was okay. So, this is the velocity relationship, okay, and this is essentially x. Okay. So, over x, what is the relationship of the velocity? So, you can see it is a linear relationship. If you see from that, from this particular equation, that the velocity here, rest everything is constant, the velocity and x is a linear relationship, right. So, therefore, within this region, so okay, so within this region, okay. So, essentially what you can say, what basically we are saying is that we have the a velocity which is u3, okay. and then that linearly decreases to 0, right, as the expansion fan moves into the quiescent region. Okay, so that is the velocity. So then let us now next look at, say, the density. Okay, now let us then look at, say, density. Again, this is all x. Okay, so let us say this is, say, density. Okay, now rho 4. Okay, there is some density here. So say this is rho 4. Okay, and rho 3. Okay, now rho 3, rho 4 by rho 3. So in here, I think we will have to kind of do the numbers, calculate something by numbers, and then you will see, like we had seen for the shock wave, as to whether the pressure decreases or increases. In this case, I can say that the fluid here is moving in here, right? The fluid is moving to its right. So u3, the velocity of that is this way, okay, and therefore we did see minus characteristics, right? So the wave is actually, so this is the movement here, this is here, but the particles within the wave are moving opposite to it. Hence we had within the wave, sorry, within the disturbance is moving away from the wave. So therefore we had C minus characteristics. So that is the reason why we will have, okay, now the density will decrease in here. Okay, so density is, say, rho 3. Okay, so rho 3, this is rho 3. Okay, and if you come here to this this expression over here, so this is the relationship of the densities, and you can replace this by the x relationship with x by t here. Okay, so what we get is which is a nonlinear variation of the density within the wave. Okay, so so yeah, okay, so we can, I think, write that any point within. So this is u, this is rho. Okay, so again, if I similarly, if I draw again x, and let's say this is the temperature. Okay, so similarly, now this will kind of follow, I guess. This is T4, okay, and then we have T3, and again this is a nonlinear relationship. Okay, so you can sort of see from there, and again finally the pressure. Okay, so then we have pressure, right? So P4, okay, we have P3, okay, of course this is equal to P2, that's all we know, okay, and again in here we have a nonlinear relationship. Okay, so therefore this is P. Okay, so therefore what we can see, so these are essentially, if you look at this relationship, so this relationship, say if I call 1, okay, so let us say I call this as so something, okay, so the velocity, basically velocity, we plotted this using this relationship, and these are rho, t and p with 2, 3 and 4. Using equations 2, 3 and 4, we were able to kind of figure out the nature of the changes within the expansion fan, and behind and aft of it. So essentially what we've done so far is that we've been able to calculate the change of properties in the entire shock tube. Okay, and we've derived expressions using method of characteristics in this particular case. So, method of characteristics is something that we will do now in a little detail and apply it for some more different problems, and we will see how that works. So, in this case what we just to sort of summarize this, okay, in this case what we therefore saw was that this expansion fan is it basically results in straight line characteristics, okay, moving left, okay, which was negative essentially because my fluid, okay, the disturbance here is moving away or in the opposite direction to the fluid here. When the diaphragm is broken and the shock starts moving to its right in this particular case into the quiescent region, it sets this fluid which is behind it into motion as well. It induces velocity there. So, this starts moving to the right, however an expansion fan therefore travels to the left as a disturbance, right. So, therefore, the particles within the expansion fan, okay, they are moving to the left while the fluid in totality is moving to the right. Okay. So, and that is something that you can see represented in the properties. Okay, as the velocity decreases, okay, is an isentropic process. It's an isentropic process. So, as the velocity decreases linearly within the expansion fan, and then the density, temperature, and pressure all increase as in a nonlinear manner. Okay, nonlinear manner. It's an isentropic process, and therefore reach the constant values in this quiescent region. And we found out that the characteristics for these are straight lines, which is, and this is centered because they originate at the same point and move into the quiescent region. So, it's a simple wave. Okay. Now, we will see different applications of these characteristics, like I said, okay, when we continue the next couple of lectures. And also what we saw here for the shock wave is that this is an unsteady motion, right. And the way we solve for properties in this particular case is basically change the reference frame, okay, to change the reference frame so as to do so as to get a picture which we were familiar with earlier, which was the steady case. Okay, and for that all we did was superimpose these two regions in here with a velocity which is exactly the same in magnitude, but opposite in direction to this the velocity of the shock wave, and with that we were able to calculate properties behind and in front of it. Okay. And what we've seen here, of course, is that unlike in the steady case, where the incoming Mach number governs the nature of properties behind and after the shock, in here that is governed by the pressure ratios across the shock wave. So similarly, so for a given diaphragm pressure, right. So initially when we have the diaphragm, we have a pressure, we have just this region 4 and 1. All of this is not happening at the time. So then we have a pressure, say P4 and P1. Now, if for a given pressure there is a given shock strength. Okay, so shock strength, and using that we can therefore calculate these the properties across it. Okay. So, all right, I think that's all about the shock tube. What we shall go further with is some more applications of the method of characteristics. Okay, thank you.